The first thing I would like to say is that you can see three names on this presentation and on the paper. They made me come up to do the speaking, but the work is mostly Jonathan Manktellow's. Most of the good ideas you will see in here are Jonathan Manktellow's, so it is fitting that his name appears in the proceedings as the first name. And Morten and I have been just occasionally twitching on the rudder to point in what we consider the right direction. So I guess if there's anything wrong with it, it means we didn't twitch the rudder. If there's anything right with it, it's Jonathan's call. And also, as you'll see in a moment, Phil Last is to blame. Where's Phil in the? Where's Phil? Did he go see? Phil Last is to blame for some of this. So I'll say this as we come on. Right, here's the problem. APL Sharp, if you've seen any of the other presentations this week, is a new venture. It's an APL-like language that we hope will appeal to current users of Dyalog and other array languages. Our mission statement has been to produce a language that is commercially attractive to Dyalog users. Clearly, we like to eat, so we want something that is commercially viable. It's pitched at working in what we see the future as the .NET and related frameworks. We think this is the way computing will be, and in the past APL has been a very insular system. APLers didn't like to go very far outside their session to talk to the outside world. Over the last couple of decades there's been a fair amount of effort in the APL communities to reach out to other systems, but this I think is the first APL system that I'm aware of where it's been designed from the ground up with the view of being a good citizen in the global framework community. So APL is just another way of writing your programs. So what we foresee is that people will use different technologies for different parts of their application depending on the suitability of the technology for that particular part of the application. So if you're doing maths with arrays, then you may choose to use APL for this part. If you're doing, I can't think, graphical stuff, then you may choose to use some other frameworks, other parts of the framework, other software products available to the framework. And this is nice because it leaves us, the implementers, free to do what we consider we're good at. We know how to reverse Boolean arrays and do this sort of thing. We're good at the APL engine. Now let me just show you one of the. This talk is specifically. It's about a problem we have in. Well, let me tell you the problem. In Dyalog, we have two distinct function definition forms, and we call these tradfns or T-Fns, which are traditional APL header-line functions, and we have D-Fns, which are in my terms relatively recent, only a decade or so old innovation. It's as if it were yesterday. What I'd like to do is this is Euclid's greatest common denominator algorithm coded as a traditional function. And you can tell it's a traditional function. I wonder if you can see the mouse pointer. Can you see the mouse? Oh yeah, there you go. So I can use this as a pointer. So a traditional function, you can tell it's a traditional function because it has line numbers down the side and it's got dels. And this is the way we're used to seeing these produced. A traditional function has a header line, and the header line defines the syntax. So when we look at this, we count the number of names. First of all, we identify this arrow, which is a separator, and we can tell it's a result returning function, and the result variable is z. And then we count the number of names along here. There are 3 names. One of them must be the name of the function. If there are three names, it's the one in the middle, and it's a dyadic function. So the name on the left is the left argument, and the name on the right is the right argument. If it just had two names here, it would be a monadic function with a name and a left argument. So if we hid the M, and if there were just one name, it would be an niladic function. So that's the first thing. So the header line is quite busy. In my opinion, it was a masterpiece of design in its time. It was because it mirrored the calling syntax. And then in this function, we can see that we go round in a loop while n is still non-zero. Until n is 0, we modify these variables. We set m to n, and we set n to the n residue m. We go round until n is 0, and then on the last line, we set the result variable to the absolute value of m, and then we fall off the bottom of the function which returns. So this is Euclid's GCD as a traditional function. And the points to observe in this are that traditional functions, first of all, they combine function naming with its definition. The name of the function is printed in the function header itself. So as you define a function, you also name it. They name any arguments. They name any result. They must declare any local names. And control structures. When I said that was a traditional function, even more traditional was before control structures, we had a branch arrow. But it amounts to the same thing. Control structures determine the order of execution of these lines. And let me just flip back to this thing. One of the things I'd like to say about this is that when I read this function as it's executing, I said that m is replaced by, m is updated, update m, update n, do this, do that, go round. Traditional functions are doey functions, we do things in them. And so traditional functions encourage a procedural style of programming. They don't mandate it, but they encourage it. We go into a do this, do this, do this, do this. Now in Dyalog we have a D-Fn, and this is a coding of exactly the same algorithm. And when we're reading a D-Fn, we don't say do this, do that, we say is. So this says if omega is 0, the result is the absolute value of alpha. Otherwise, the result is omega GCD, omega is alpha. It's easy programming as opposed to doey programming. So you can see these two styles are very, very different. D-Fns, first of all, separate function naming from its definition. In the same way that when we have an array, if we have an array 1, 2, 3, that's an array. If we want to name it, we say a vec assign 1, 2, 3. So the specification of an array is separate from its naming. And the same is true with D-Fns. We separate the naming from the definition. So D-Fns separate function naming and definition. Its arguments are special tokens alpha and omega. The function result is implicit. We don't have to say colon return the result. We don't have to say make a special variable the result. The result just is an expression. Assigned names are local by default, as opposed to having to specify it. The guard, the colon, is the only control structure. And D-Fns encourage a functional style of programming as opposed to a procedural style of programming. And here's a slightly larger D-Fn. We'll show you this. This is a function to return the real roots of a quadratic equation. This function used to be called roots, not real roots, because until recently we didn't have complex numbers in Dyalog, so we could only tell you the real roots, but now I have to call this the real roots. And what we can see in here, this is a D-Fn. We can name we pass a vector argument, we name the parts of the vector, we calculate, I believe this is called the discriminant, b squared minus 4ac, and then depending on whether that is positive, 0 or negative, the quadratic equation has 0, 1 or 2 roots, real roots. So if d was less than 0, we don't have any real roots. If d is equal to 0, we have 1 real root. If d is greater than 0, we have 2 real roots. So it's just an example of the structure. It's a good example of the working parts of a D-Fn. And you can see this is very different from a traditional function. I'd just like to hammer this out. This next slide is one. Just like to hammer this out. The difference between the specification of a function and the naming of a function. They're bound with trad-Fns, but in D-Fns, here is a function applied to an argument. The function is specified inside the curly braces. This is a function that takes its argument and makes a pair, a vector pair from it. So here is an application of a function to an argument. Here is a naming of a function. We name a function in the same way that we name an array using the specification arrow. And to complete the cycle, here is an application of a named function to an argument. And when the interpreter is evaluating this, effectively it takes this line and it converts it into this line and applies the function. So we call this dereferencing. When the interpreter finds this name, it looks up this definition, converts it to this, and executes it. Now, so it's a really easy job. We've got these two completely different paradigms, completely different ways of programming, and the only thing we have to do is to combine them into a single beautiful unified whole which is greater than the sum of its parts. That was the job. So what we want from APL Sharp function, I'm calling them A-Fns in this, we want to share the cleanness of the D function style, ideally. We want to be able to provide both procedural and functional styles, because for a lot of real life programming, it's important that we can do procedural programming with side effects. It's very convenient to allow unnamed functions and operators as well as named ones. So we would like to allow both. We want to support the optional naming of arguments because that's handy. Sometimes it's nice if the arguments are named rather than just alpha and omega. Sometimes it's nice to give meaningful names for these. This is a big one. We want to allow both control structures and guards. You can achieve everything with a D function guard, but sometimes it's conceptually more easy to have loops and if then else's and repeats and whiles and cases and selects. Oh, I didn't say, please ask questions as we go along. What I'd like to do is finish a little ahead of time to allow some discussion of this, but if there are questions that arise as we go along, please shout out. Okay. And we need to, D-Fns assign local names by default. We'd like to allow you to assign both local and global names. So how are we going to, okay, and so A-Fns will allow both procedural and functional styles of programming. So this is all we have to achieve.
John, do you support strand notation in the arguments in the result?
Yes, watch this space, as somebody said this morning. Well, hang fire. Okay, so here's what we're going to do. I'll show you a little thing. An A-Fn. This is what an A-Fn looks like. It's a function within curly braces. If it's a monadic function, we have a right argument and then an arrow and the body of the function. And the right arrow is pronounced maps to. So effectively we say right argument maps to this body. If it's a dyadic function, then there are two things. In the signature, we're calling this a signature. Everything to the left of and including the arrow is the signature of the function. So if the signature has one name in it, it's a monadic function. And if it has two names in it, it's a dyadic function. It's just like the traditional function you counted, but with a traditional function you had to subtract one to see whether it's monadic or dyadic. This is easy. You don't have to do this subtract one. It's just one or two names.
And if you have a Dyalog case?
Sorry?
The Dyalog case?
There is a Dyalog case, and we were hoping that nobody would say that. But can I leave that to the end? We'll address that at the end. There is a Dyalog case, and we'll address that at the end. There's a technical problem with providing a Dyalog function, and we'll show you how to do it at the end. Okay.
And if you have three arguments, you embrace them, and you have...
No. Okay, I haven't really... in this case, the first... this first argument, this rag can be any array. It's like in a traditional function. So it could be a 1 or 2 or 100 item vector. Yeah. It's like a traditional function. Now here's an example then. So my dupe function, written in APL Sharp, would be... The function itself is specified between these braces, and it says A maps to A space A. And in this case, I've named the function as well. I didn't have to do that, but it's just to remind me what it does. So here's an APL Sharp, fully paid up APL Sharp function.
That function doesn't look like it's coming or going.
Yeah. Yep, that's right. Yeah. But the thing is to remember the right arrow is maps to, and we don't have a branch anymore in APL Sharp. He's looking for Jonathan.
Yeah, that's right.
You don't have a branch, no.
We have go-to control structure.
We have a colon go-to control structure, so that if you see a right arrow, that means maps to. Here's another function. There's a function for the square root. So there's one thing in the signature. So that is a monadic function. This is a monadic function. N maps to n to the power a half is a square root function. And this guy is a dyadic function because there are two things in the header. So it's a dyadic function. So it will take a left argument called m and a right argument called n, and it maps to n to the power reciprocal of m. So that we could take the cube root or the fourth root. So 3 root 64 would be the cube root of 64. We're coming to this as well. Okay, I think I've probably got if I had my slides in the correct order, I would answer these questions before you ask them, but I don't. So just bear with me a moment. Okay, I'm going to take a... Don't let me do more than 4 minutes on this, because I have to show you this. My son wrote me a little toy, which I'm going to show you. Let me make this big. Oh, and it's a little big. Here is a traditional... It's a... I don't know if I can make this smaller. I wonder if I can. Let me just risk. Yeah, there you go. Here is a traditional function written in... Can you see that? And I'm going to show you how to convert this into an APL Sharp function. So there are 3 things in a header. So, the first thing I'm going to do is remove the line numbers. This is fuzzy felt. Okay, so I can do that. Yeah. The next thing I'm going to do is replace these dells with curly braces. And up here somewhere I've got a curly brace. Yeah, so you'll see this gets... so let me put that one down there. In an APL Sharp function, I don't need to give an explicit result variable. So the last thing is the result. I don't need to name it, so this goes out. So instead of there being... Oh, and sorry, because I don't need a result, I don't need this. So it gets simpler. Variables are local by default, so I don't need this. So it's simplifying all the time. And now the two things in the header, because it's dyadic, this can move over here. And if I want to name the function, I can put this here. Oops. And then the only other thing I need is the maps. So this is a, and I believe that's a fully paid up APL Sharp function. I promised him I'd show you this. He spent a long time writing this one. Yeah. Okay. So you can see that there is a straightforward. If you will it execute? Yeah. Would it trace? Okay. So you can see, effectively, the point I want to make here is there is a good correspondence between the traditional function header and the APL Sharp header if we move the naming outside. I think I have to buy beer for this. Right, let me go back. So I'm going to go back to. Now, can I start this again? There's got to be a way of. I'm not. Those of you who know me well will know I'm not computer literate. A slideshow. Let me see. This may start at the beginning, in which case I'm going to zip. Oh no, here we go. Right. Okay, so yes, let me just go through here. So these are the functions we've seen. I'm going to show you the GCD example coded in an APL Sharp function. So again, it looks very much like the D-Fn, and the only difference is that in the header, instead of alpha I have M, and instead of omega I have N, but otherwise it looks very similar to the D-Fn. And in fact, we found we were able to remove this signature and say if you don't have a signature, then it is as if you had specified alpha omega maps to. So this function is also a fully paid up APL Sharp function where, because I don't have a maps to, it assumes I mean alpha and omega. And what this means is that most simple D-Fns will translate directly into APL Sharp. So you have a little more work to do with your trad-Fns. So say.
Can you have monadic?
Oh yeah, in fact all functions are ambivalent, so we'll come to that. Yes, they are ambivalent. All functions are ambivalent in APL Sharp. Yeah.
Not monadic. So you cannot have monadic.
You don't have a strictly monadic function. No. Sorry, that's it. Yeah.
Presumably, single name in a signature must false monadic.
Yes, and the rules keep. I can't remember what we do this week. So if you give a left argument to that, you get an error in the calling line.
Being explicitly monadic, it's only monadic. If you don't, it's either dyadic or no header, then it's unbound.
Okay, but if you have a strictly monadic function like my square root function, if I were to supply a left argument, that would be syntax error, and presumably in the calling line, it would blow up before calling it. Yeah. Yeah, right.
How do you tell that? If just monadic or a dyadic function, you just never use the left argument?
No, if you're giving a specific header like this, then you can tell the valency of the function. If you omit the header, then it's an ambivalent function, and alpha and omega are both available. If there is no alpha, then you get a value error. Well, actually you don't. I'll come on to that in a moment.
Yeah, well, that was the point. If you don't have alpha,
Yeah.
then how do you know it's not a dyadic function for which you just didn't use the left argument?
Just let me get. This is like a politician. I'll ignore your question and just answer a question I happen to know the answer to, if that's okay. If you give an explicit signature, then it's clear that what the rules should be. Yeah. If you omit the signature, then effectively what you're saying, it's an ambivalent function that will try to evaluate its left argument, if there is one, beyond at call time. It's like a D-Fn. It's exactly the same as a D-Fn. Jonathan, shout if I'm getting this wrong.
Yeah, that's right.
Yeah. So it pretends it's a D-Fn, which is ambivalent. If you're not, maybe, yeah, not
Later.
later, yeah.
If I want to define a monadic polynomial,
Yeah. Then,
A-Fn,
yeah,
using alpha and omega.
you can't. No, you have to.
You can't even just say omega?
No, I don't believe so. I mean, one of the things is this stuff is up for grabs. I should have said this in the introduction. This is a work in progress. If I hadn't been so lazy, we would have published the draft spec on the internet before we came to the conference, but I slipped on that project. When we get back, our plan is to put the draft spec for APL Sharp on the Dyalog website and invite comments and take the ideas of the community as part of this
I
process.
believe we ended up saying you could write omega against to define it explicitly.
Okay, yeah.
The last time that's what
Yeah, but there's very many iterations, but okay, you could be right in that case. Yeah. So effectively, this is like a D-Fn, except for the obsessive compulsives like me, it preserves the space here. Hey, so I can line up my vertical bars, whereas D-Fns in Dyalog at the moment throw your blanks away, but APL Sharp preserves them. So that in itself is a good reason for... yeah. Okay, Phil last. Where is Phil? Did he sneak off? Oh yeah, he's hiding in the back. Phil last is this Gandalf figure that we're the hobbits. We run around doing stuff, and occasionally Phil will appear in his grey cloak and say, "Please don't do it that way." And we've learnt to take notice of this. The first thing that Phil last told us, in Dyalog 13, we have the primitive functions left and right, or lev and dex, and they're using the tacks, and the right tack ignores its left argument and returns its... Let's see if I can do this from your direction. That's a right tack. Is that right? From your direction, that's a right tack. It ignores its left argument if you give it one, and it returns its right argument. If you only give it a right argument, it returns it. The left tack, if you give it two arguments, it returns you the left argument. If you only give it a right argument, it returns the right argument. Okay, and Phil said, please do it this way. I wanted to give an error, value error, a syntax error, go away error. Phil said, please, in this case, just return the right argument. And I believe that Ken had appeared to Phil in a dream. Ken published this specification in 1985 or something. Ken said, do it this way. So the left tack, the left primitive function, if you give it two arguments, it returns the left one. If you give it one argument, it returns the right argument. So what Phil said, if an A-Fn is called with only a right argument, and it doesn't have a signature, so it gets into here, then please operate as if somebody had said alpha is right tack. Okay, I'm coming to the tacks in a moment. Please treat it as if alpha behind the scenes had been specified as right tack. Just do that and see it's one of it. And the wonderful things that come out then, you know, in traditional APL we have a first line that says execute 0 equals quad nc quote larg quote slash larg gets 0, which means if there wasn't a larg, set it to 0. And there are more sophisticated ways of doing that. But very often we need to give a default value to larg. So how we do this in APL Sharp is to do this. And what this says is if an alpha has been given, then return it, name it larg. But if an alpha has not been given, then it's going to be a right tack. So the left tack will return the 99 and so will the right tack. So this is the equivalent of larg equals execute 0 equals quad nc doody doody doody. Yeah.
Is this a special syntax or this means that I can use alpha also if it's not defined?
Oh yeah, you can use alpha anywhere in your function, and but it has the value of right, the primitive function right, and these are just some idioms. So this is the way you specify. In fact, it's much nicer than this. Alpha left tack 99 can be used anywhere in an expression, not just to name an alpha, but it can be used anywhere. And it says if there's an alpha, use that. If otherwise, use this value. So it's much better than the D-Fn alpha assign syntax. It's much nicer. Sorry?
It's a function.
Yeah.
So it's somewhere down below I use alpha
Yeah.
in a way that requires it to be an array.
Well,
I die.
you die. Yeah, but you die. You die anyway with it. Yeah, but watch. This is called. No, there are three things.
Okay. I want the default value
Yeah.
also to be named alpha. I mean the old default.
You want to default to an error or something, I guess. Do you?
No, he wants to be able to write alpha gets.
Oh, I see. Okay. Yeah.
Left, right.
Yeah. That's Jonathan will do that for you. We don't have that. This is what we have. But this is a good suggestion. Thank you for that suggestion, and we'll. Yeah. This is why we're giving this presentation.
Because on one decision they made, I think it would be very dangerous to say alpha gets something because they want to call function by reference.
I tell you what. Let me go a bit further, and we'll come back to this at question time. I thought this would only, as ever, last 10 minutes, but I talked too much. So that's how you specify, using this technique, this is how you specify default left argument value. This is how you specify Boolean. This is a trick for monadic is a Boolean 0 or 1. It's 1 if the function's monadic, and it's 0 if the function is niladic, is dyadic. And I'll leave that as an exercise for the student to figure out. Well, if alpha is an array, then this thing here, let me use this stick, give me a feeling of power. If alpha is an array, if alpha is supplied, this is a 3-item array, so the first item is 0, so it wasn't monadic. If I supplied an alpha, then this expression returns a 1. So if I supplied an alpha, it returns a 0. Hang on, it's exactly, yeah. If I didn't supply an alpha, so it's a monadic function, then this returns its right argument, which is 1, and the first of 1 is 1, so it's monadic. Yeah? Right. So it's a little idiom for doing this. And then this sort of relates to Roger's point. The next thing is very often, within an ambivalent function, I want to pass the ambivalency to a subfunction. I want to say, if I wasn't called with a left argument, I'm damn well not calling you with a left argument. So in this case, if I call alpha sub omega, if alpha was defined, it's a left argument. But if alpha was not defined, it's right. So sub is then called in monadically. So those three cases do a lot of the work that we do when we're dealing ambivalent functions. Let me rattle on. Okay, right. Another departure in here is an APL Sharp function which is being applied to 0. D-Fns. A D-Fn is an expression preceded by definitions used in that in the expression. Or another way of looking at it is a D-Fn executes making local names until it comes to the first unnamed result, and that exits the function. That's another way of looking at it. So in a D-Fn, if I put any lines after that expression, they're ignored, they're wasted. And I think Phil Last exploits this in his palindromic expression for phi, which is on YouTube. There's one extra segment which isn't used, but it's there. In a departure, we are saying in normal traditional APL. In APL Sharp, it's the last expression. If I have many expressions, 2 plus 3, 4 plus 5, 6 plus 7, it's the last expression that's executed, which is the result of the function. And the other thing is that if I don't assign a result, in traditional APL, that result is dumped in a session. So if in the middle of my trad-fun I have 2 plus 3, and I don't assign it, that dumps the result of that into the session. In APL Sharp, that is ignored. It's just it goes into the wherever all the 5s go in the sky. Sorry, the bit bucket, yeah. So this is a little function to demonstrate this. If I run this function, this will display in the session. This vector will be displayed in the session. This vector, unless it's the last, will be discarded. And the final, that's the whole function. The final result will be returned. So this function, when it's run, will display this in the session because I'm saying quad gets. This will be ignored because it's an unassigned result, and this will be returned as a result of the function. And I desperately tried to make a couple of extra PowerPoint animations to show this working a moment ago, and I wasn't clever enough. But you have to, if I were to run this function, on the next 2 lines I'd see display and return if I ran this function. Okay, now this is mopping up one of the questions. Tuples. This is the first bit of the roots function, the real roots of a quadratic, written as an APL Sharp function. So it's monadic. I give a 3-item vector, and typically what I would do is assign the 3 separate variables, A, B and C, to the argument. I'd split the argument out, and then I'd carry on with my calculation for the real roots of a quadratic. Okay, one of the things I can do here is an additional thing, is that I can move that splitting of the argument up to the first line if I parenthesize it. So this is how we distinguish between there is no triadic functions. If I took those parentheses out, it would be an error because we don't have a triadic function. The parentheses say this is one thing, so this is a monadic function, and it just saves me this line, this naming line, which we do a lot in D-Fns, so it's slightly neater. Yeah, so this is computer scientists, I believe, call this a tuple. I'd only read about this stuff for decades. I knew all about tuples, but I was pronouncing it tuples. And I gave a lecture to some computer scientists. They fell about laughing. They said, no, tuple, granddad.
Only one question for the designer, then consequently you need a tool and a bracket expressions for a dyadic function.
Yeah, and it's better than this because here is, let me show you what...
Wouldn't then the better design have been the semicolon between the left arc and right arc?
We went round that route. We have spent a lot of time arguing whether it should be a semicolon or a vertical bar or a del. And in the end, we realised we didn't need anything. So it's the same as a trad fun. You count the things. If there's one thing, it's monadic. If there are 2 things, it's dyadic. It's like when you try and parse the header line of an APL2 operator. You count the number of things. If there are 3 things, it's a function. If the middle thing is got parenthesized, then it's an operator with its operand, and it's easy to parse. Let me show you an example. These tuples. Here is another monadic function. This is a right rotation of a binary tree. If you represent your binary tree as nested vectors, this does a binary tree rotation. It's a monadic function. There is one thing to the left of the mapping arrow. So that's a proper that's a right rotation of a binary tree written in A-Fn. And this can be let me see. This is a larger example. Anybody know what brainfuck is? There's a programming language called brainfuck, and this is the header line of brainfuck written in A Sharp. So what we see here, this is a dyadic function. Its left argument is a vector pair whose first item is a vector pair, and so on. And this does a lot of work for you. So this is an extreme example, but it just shows you that the syntax is completely well defined. And clearly, it's a matter of taste how far you produce this. Okay. Names are local by default. So this specification makes a name that is local to my function. If I want to make a global name, then I make a space assignment like this. And I think that's the right way around. Global names, we really want a bit more noise in the syntax to say this is a global specification. So this is making a global assignment in this case the root space, but there is another squiggle that is quad jot, which means the current namespace. So I could say, if I said quadjot.aa is names 456, this would be in the current space. So this is how we distinguish between local and global assignment. I'm going to go a little bit quicker so that you get all your questions lined up. A-Fns allow control structures, but in addition they allow control structures to be expressions, control structures to return results. So they're not just void returning. So here is an example of a control structure that says I'm going to add 1, 2. If 2 is less than 3, which it isn't, 4, else if 5 is less than 6, which it is, so I'm going to add 1 to 7, and then add the result of that to 9 at the end to get a 17. So control structures can be part of expressions.
Would you consider adding a new control word called then?
Then?
Yeah,
Oh, okay.
That would permit you to put all of that on one line.
Okay, I can't think through the consequences. I'm not clever enough to think through the consequences of that, but you may be right.
Right now, that's the only thing stopping you from putting it
No, you still need diamonds to put that on one line at the moment. All of these line feeds are significant because you can't put the 7 on the same line as the 6 clearly.
But you could put a diamond.
You can diamondize it at the moment. You can put diamonds.
Okay, so you already have it.
Yeah.
Yes, use diamond.
If you use diamonds instead of new lines, it works. Yeah.
Roger, syntactically, the guard is there. Semantically,
Yeah.
guard.
The
Yeah.
question really is, can I put all that on one line?
Yes.
Yeah, you can. Yeah, with diamonds you can. So that was control structure expressions, and then you have the equivalent guard. This is the same thing as guards. Then that's exactly the same expression, but using guards. So guards can, in D-Fns, guards cannot be expressions, but with A-Fns, they can be expressions. They can be embedded in larger things. So that's we get that free.
When you say they can't be expressions in D-Fns?
No, guards cannot be in parentheses. You can't put a guard. You can't put a whole guarded expression. You can't put the condition colon something diamond something else all in parens in D-Fns.
Only parens,
Yeah.
but it's cursive.
Yeah.
So obviously here, can you put everything on one line with diamond?
Yeah.
Okay.
Yeah.
But you wouldn't have a diamond after the left paren at the top.
No.
So in what cases do you have to have a diamond? What cases do you not have?
Well, effectively, a diamond is exactly the same as a new line, so when you open a paren, you effectively can new line your way until the next paren.
Parens and curly brackets,
Yeah, parens and curly brackets. Effectively, parens are now got the same sort of power as curly brackets. But the difference is curly braces consume values and parens provide values. The braces are consumers and parens are providers.
There's another big difference, it's the names.
Yeah, the name, yes, the name, there are other differences as well. Stop it. Okay. Now, I'm going to do this this quickly. Functions and operators. We had functions. How about operators? This is really very, very quick. Here's a niladic function. Here's a monadic function. Here's a dyadic function. I'll do the rest of them and then explain what's going on. Here is a monadic operator returning a monadic derived function. Here is a monadic operator returning a dyadic derived function. Here is a dyadic operator deriving a monadic function. And the final one is a dyadic operator deriving a dyadic function. This was a masterpiece of design by Jonathan. We spent ages designing more complex syntax for this. And Jonathan said what we can do is distinguish the operands from the arguments by curly braces. So this is, I'll show you a couple of examples, but effectively this is the signature for an operator contains curly braces.
Is the third line there really right?
No, it's not. It's wrong. The M should be on the inside here.
Oh, it should be an N. Yeah, scratch this.
Could
Yeah.
we get an access argument as well?
Sorry?
An access argument?
I don't think so, but I'll check. Sorry, this M is an error. It should be an N on this side. I'm sorry. I didn't proofread my slides.
Or an M on the side.
Could be an M, yeah. Okay. So an example, here's an example of a function that applies its operand f to each leaf in a nested array, each depth 0 leaf that says if it's depth 0, apply the function, otherwise apply this recursively to each subarray.
Again, there's no diamond at the end of that line.
No, a new line is as good as a diamond. That should be a
Another case.
change is as good as a rest. Yeah, that's right. That's a good point, though. Yeah.
Are we terminating at the second line if the condition, if the guard is true?
If the guard is true, that's the result of the function. Yeah.
So it doesn't,
Yeah,
it doesn't
yeah.
carry on.
Yeah. Otherwise, otherwise it drops through, and the last line is the recursive call. Oh, sorry.
If an assignment on the,
How does it go to return?
When it hits the bottom like a trad fun, it goes.
The F of A.
F of A, it's returning the F of A.
Oh yeah, because the guard fired, then it's
Also, there's a guard.
yeah. If it's a guard, it fires. Yeah.
It's like a D-Fn.
Yeah, it's like a D-Fn in that case. Yeah. I mean, you could find a bug in this design, but I think we've thought that through. I'm going to skip this. Oh no, I'm not. This is a slight difference from a D operator. With an operator, you are obliged to give a syntax. You're obliged to give a signature. With D-Fns, an operator is distinguished by the presence of alpha alpha or omega omega somewhere in the body of your 1,000-line operator. With this, to distinguish an operator, you cannot omit the signature. You have to give it. So this is an A operator. Let me just say. So to turn a D, this is a D-Fn, a D-op. To turn it into an A-op, you are obliged to give the signature. So it's not too difficult. So to summarise, with minutes to spare, and then we'll have a. I've put in my notes an argument. So in summary, right. A-Fns, and they need not be named. The functions and operators need not be named. They can be anonymous. They begin with an optional signature. If you omit the signature, it's assumed to be an ambivalent function. They terminate after the last line, all an explicit return statement in this case, and there are a number of ways of terminating, but by default they terminate with the last line that's executed. They do not display unassigned results. They allow both control structures and guards.
In your last slide, you need A-Fns and A-Ops.
Yes, A-Ops, I'm sorry, another typo, I beg your pardon, yeah. A-Fns and A-Ops. What can let me just get this, yeah.
Are operators obliged to take functions, or can they take data?
They can take arrays. They can take arrays as an operand can be an array or a function.
Okay. And can you extend the syntax with the parenthesis and the multiple assignments at that level?
And it's Jonathan's got this handy phrase, version 6, he says, when we say things like this. But the intention is yes. Because a lot of APLers use operators to write triadic and quadratic functions, an ability to pass 4 arguments. So there is quite a market for array operands to operands, and there is no structural reason why we can't use tuples as to receive array operands. Yeah. Yeah, Roger.
One of the slides says names are local or
Yeah.
something. Can you explain a little bit what local means?
Oh, yes, okay. Local in the same sense as D-Fns, exactly the same sense as D-Fns, in that you can have nested nearly, there's a point here. With D-Fns, you can have nested functions, and with A-Fns, you can have nested functions. And when a name is assigned, it's local to the nearest enclosing curly braces. And so when that function exits to an outer function, that name goes out of scope. Now, one of the things with a D-Fn is that is completely dynamic. The name is shadowed at assign time. So if I have in a D-Fn, if I say I assign I plus 1, what happens here with the D-Fn, this is, I've never dared tell anybody this before because it's awful. This references a global I, makes a local I, and sets its value to the I plus 1. So these are different variables because this is dynamic. Sorry? Different scope, yeah. And the proposal is with, I think, you just shout or throw something. The proposal with A-Fns is that at quite a fixed time, it looks for these assignments and effectively declares at that time. So this would be a value error. And that's for 2 reasons. One is it's, I think, more hygienic. It's better for the language. But the other thing, it gives Jonathan a much better route to compilation down the road a piece.
How do you address the root namespace and the namespace where the function is in it?
Yeah, the root namespace is addressed with this hash or pound symbol. That's the root space. And then, let me see if I can draw this. Is it called jot? Yeah. This symbol is a Unicode, in the APL part of the Unicode set, means the current space. In Dyalog, we have a system name quad this, and these are the same. So I don't know how we're pronouncing this. Supposed to pronounce it this. So we'd say this dot vec is assigned. Would name a global. Would make a global name in the current space. Yeah. One of the as a side. what part of my job is to be negative and grumpy and complain all the time, and one of my current things is I'm very careful to say, please don't invent any new glyphs that don't have an obvious overstrike, because we can't afford to keep getting the physical keyboards engraved every time. So we've put as many engravings on the Dyalog keyboard available at this conference for €100. See your local sales representative. There's a nice cherry keyboard with symbols engraved on, but it will work with this because there's an obvious overstrike for this glyph. So we have a certain amount of leeway. As long as there's an obvious overstrike, it's okay to put it in APL Sharp.
So if you want to assign the I to the global I, then you have to put this symbol and a dotted I.
Yeah. And I think that's good because from a functional programming point of view, that's an unusual thing to do, to make a global assignment. So it's nice that it is a little bit noisy when you're doing it. The clean stuff is...
You have to have a circle, then a jot, and then a dot.
Oh yeah, a circle with a jot and a dot. Wouldn't that be good overstrike?
This.
Target.
Yeah.
What about execute, when you execute something inside the method?
Using the execute primitive. This guy, you mean?
Yes. Do you execute in the global environment, in the global scope, or inside the...
I don't know the answer to that question. I don't know if any of us know the answer to that yet. That is one of the things. This is not a complete specification, and these things are very difficult to decide what is best to do. We don't know. Because executors, Jonathan would pretend that this didn't exist, because if he's trying to compile things, his life is not happy. But well, clearly, I believe there will be an execute.
I believe it executes as if it was written in the function.
Okay.
That helps.
Well,
In the function, if you're executing in the function, the current design will be evaluated in the same context.
Yeah, it does, as if that expression was.
As if it was just.
so he's going to do dynamic localization of any. So if I say execute A is 3, that will make me a local A.
Yes.
Oh, that's very clever. I'm glad you're implementing this.
But if you compile the code, that'll be an error. Well, simply execute will not be there if the code is compiled.
Okay. I don't really understand that, but there you go.
The argument to execute the namespace.
I mean, the argument is not, typically it is not a literal value. It's not available at compilation time. The argument to execute. If I do execute only, I don't know. But these are good questions. Okay. All right. Well, thank you for your patience and come back. Oh, so please, this is a formal request for feedback on this continuing design. Watch the Dyalog website because we.
The APL Sharp.
The APL Sharp, so aplsharp.com. All one word.
Yeah.
Like this. Thank you very much. Thank you.